to talk about a few things that are building us toward looking at TEFRA2. So what we'll do first, remember last week I talked about the diffusion equation and how you use the diffusion equation in modeling, and we did some very simple experiments ending in a 2D solution. So I'm going to go over that really quick because it's obviously, you know, a little complicated if you're not used to that sort of thing. And then I'm going to go on to introducing something called the advection equation. You can think of that also as the continuity equation. It's got various sort of manifestations in the literature, but I'm going to use a very simple form of it to introduce it and talk about some issues actually implementing that equation in 1 and 2D. They come up because of numerical instability. And after I do that, I'm going to get to the combination, the advection diffusion equation, and talk about putting these ideas together and how we overcome some problems by putting these two equations together, perhaps introduce some more problems. And then finally, I'm going to get to TEFRA dispersion and TEFRA2, which uses a simplified version of the advection diffusion equation. But hopefully, you're going to be in a really good position to have an eye out on these differential equations, sort of begin to get a kind of intuitive sense, hopefully a more intuitive sense of how they work, how they're implemented in code, and then how we can use them to solve problems. And I definitely have a sort of TEFRA focus today, but I'll try to remember to bring up, you know, cases where we can apply these equations to other problems. You may be somewhere along the line, you had a class in hydrogeology or something like that, and in that class you ran into the diffusion equation and the advection equation and stuff like that. So certainly tools for doing groundwater modeling like ModFlow, it's very popular in the US, are based on exactly these equations. And so basically at the very core is exactly the equations I'm talking about today, and then a code like ModFlow is this sort of, you know, hero code of many features to try to make it more flexible and easy to use and to apply to a different set of problems. But at the core, it's not so complicated a concept that we can't address it and write a Python script to actually solve the same kinds of problems. So maybe you're into diffuse degassing or some other transport problem, magma flow in a conduit, or magma flow in a sill or something like that, then you can actually use these same equations. So even though I'm talking mostly in the context of TEFRA today, don't forget about those other applications. They're really cool. It makes it really useful to get a handle on what's happening with these models. Okay, so I think you can see my Jupyter notebook, right? My on Victor?
Yep.
Yellow. Okay, great.
Yes.
Okay, cool. Thank you. All right, so if you just go up to the shared read write on yours, if you happen to be running it, I put these things in the Victor short course, and I'm talking about part 6 today, which is advection and ADE. So you can grab those codes and return to your own directory and modify them or use them or just follow along as you see fit. So however you want to do that. Anyway, here's the first notebook I want to talk about is called 2D advection. And so I just put a little review in here at first. Let's take a look at the 2D diffusion equation that I implemented in code last time in the notebooks, I think notebook 4 or something like that. But anyway, we've got the change in something as a function of time. Here I'm saying the change in temperature is a function of time, but it could be the change in concentration as a function of time, or you know, some other parameter. So it doesn't have to be heat. It's a general form of the equation, and that's equal to the diffusivity which is alpha, controls how things diffuse in this particular problem, and the gradient in the temperature or the concentration as a function of x plus as a function of y. And so that reduced to a pretty simple equation, which we could implement in code. Here I'm just going to show that if delta x is equal to delta y, I'll just call that s, then this is the form of that differential equation. So we've gone from something that, has the look of something mathematically complex to understand a physical process to something that's got the look of a pretty easy algebra equation to implement in code. And the problem, one of the hassles about doing this is we have to keep track of indices. So in this case, I and j refer to grid point locations on a grid of data. And so like a map or a cross section or something like that. And k refers to time. And this equation is arranged so I can know time, I can know the concentration or the temperature in the future at the next time step at point ij, if I know all these things about the temperature at and around that point in the current time step. So that's all this equation means really, and we can implement it in code as we did last time, but we can't, do this in a wanton manner. There's actually limits on this approximation. So, you remember from calculus or somewhere along the line that, this symbology, dt t or dt dx, sort of represents the solution as the change in time, that is the time step gets very small, or the spatial step like delta x gets very small. And so we have to pay attention to that. And so we can solve that with this stability criteria that delta t max, that is the maximum time step we can take in the execution of the code, is equal to this train wreck over here. It's just delta x squared, delta y squared, divided by 2 times the diffusivity and the sum of the squares of those grids. And if delta x equals delta y, then we can just express it like that, right? S squared divided by 4 alpha. So we're okay, usually, if our maximum time step is equivalent to what I learn in these terms. It gets a little tricky if the grid isn't equal, right? If delta x changes with position or delta y changes with position. Almost always when I implement these codes, I keep the grid steps equal in both directions for the whole problem domain. It's just usually a lot easier to solve, although not necessarily the most efficient way to do it. If you've got a really big problem or you want to solve something in great detail, you might want to mess around with that stuff. Okay. Now, another equation that's really common is the advection equation. Basically, it deals with transport. So, for example, if we have a particle like a tephra particle and it's transported by the wind field, we can say it's advected in the wind field. And then we say that the change in the variable, temperature or concentration or whatever, is a function of time plus W dt dx plus v dt dy is equal to 0. And because it's set equal to 0, it's sometimes referred to as the continuity equation. Think of it as what comes in has to go out in this advected wind field. W and v, in the case of tephra, are wind velocities. So you can think of it as the components of a vector. So you can think of the wind field as a vector, which is the sum of the components. W is the component in the x direction, v is the component in the y direction. So basically what we're saying is that, if we want to look at the change in concentration with time, we're just going to look at what's around that particle currently, and given the wind velocity, what is around it sort of dictates what comes into it and how the concentration changes in the next step. So pretty straightforward with the advection equation. Turns out there's some details here which are just sort of mind-blowingly complicated, and I'm just going to go over those relatively briefly. for you. But first, let's just make the simplest assumption that we can approximate this equation the same way we approximated the diffusion equation. And so that would come out like this. If we're going to solve for time in the future, that is at k plus 1, sorry, temperature concentration in the future at time plus 1 at this grid point ij, that's going to be equal to the current temperature minus this term, which depends on W, the time step, and the grid spacing, and minus this step, which depends on V, the time step and the grid spacing. And you can see these are the components that are around that point. So at I and I minus 1 and J minus 1, you know, talking about each one of these terms. So this term, basically, W dt dx is expressed here, and this term, V dt dy is expressed here. And you can guess that there's some time, you know, step, and a simple expression might be this. I'm just going to warn you right off the bat, this is not the best solution to this particular problem for reasons I'll get into in a second. So unfortunately, the easy thing to solve here creates some problems. So let me do a simplified script, just implementing that equation, and we'll see how it does. And so here's the function that implements that equation for one time step. And so let me just skip down here to the chase so we can take a look at what's going on. I'm going to start with a starting condition, and I'm going to say I've got a block in the middle. So this could be temperature, it could be the concentration of a particle or a gas or something like that. And I'm just gonna say that initially at time equals 0, it's located there, right? So it's sort of an instantaneous source in my problem. So a square volcanic plume has erupted into the atmosphere at a given level or something like that. Okay, and so when I run through time, so that's when 0 time has elapsed. When I run through this, it actually displaces in time. So here's the solution after 150 seconds. So the square has moved off that center position and moved to the southeast. That is in the positive W and V velocity direction, so the positive X and Y direction. So let's go back and look at the code and see how we do that, and then talk a little bit about the problems associated with it. I don't want to belabor this, but it's kind of important to understand sort of how this problem evolves step by step. And I think if you get into modeling things like temperature transport or fluid transport or gas transport, it really is worth thinking about this for a few minutes. So anyway, here's the 2D solution as I mentioned. I'll come back and I'll talk about this notation a bit more in a minute, but let's just accept that that's the 2D representation of the model. The equation I showed you up at the top. And so then I'm going to specify some bit about the problem domain. This is pretty much the same as I did last time when I was talking about diffusion, but I've got a width and a height to the model. I'm just going to set that equal to 5,000, maybe probably 5,000 meters in the X and Y direction, for example. And I'm going to set a sample space or a grid spacing. Let's just say it's equal to 10. So that's a pretty dense grid, right? 500 by 500. And I'm going to set some velocities. And in this case, I'm going to make sure so this is the velocity vector. So I'm discretizing, I'm saying that I can think of the velocity anywhere in terms of its components. Often we talk about I and J components, but I'm just saying, here's the wind velocity measured in the X direction, maybe the horizontal direction. Here's the wind velocity perpendicular to that direction, right? And then these are my initial conditions. I'm saying if this is a temperature problem, it's cool at 200 degrees C and hot at 1200 degrees C. And then I just basically do some bookkeeping. I say, well, how many grid points do I have in the X and Y direction? That's what's solved in this line. And I apply that to get a handle on my maximum possible time step, which kind of works okay. Here to calculate dt, then I create my initial set of grid points. So U naught is going to be equal to a numpy array that's np dot ones that's x, nx, ny in dimension, right? So that's okay. So then every one of those grid points is going to have a value related to t cool. So if I here, for example, if I just print U naught, I think I have to run everything just for a second. Wait, do I? Where am I? Sorry, I better run this. And I better run that, and I better run that. Okay, I'm gonna run that. You can see I print out my values of 200 everywhere, right? So that makes sense. So I've built this rectangular grid, in this case a square, where all the values are 200. And then I copy that. And the reason I copy that is one of those grids is going to be the time now. And then the other grid is the time in the future. And I sort of update and swap values between those grids as I step through time. And then I set my initial condition. And here my initial condition, I just said, well, if I'm at grid point, 200 to 300 in the x direction and 200 to 300 in the y direction, that's going to be equal to 1200, right? So that's how I just plot that out in this step. And so this is my starting condition for that grid. Okay, then to run through time, it's kind of a simple code. So here I'm going to run it for 300 time steps, and I'm going to call this function. That's the one I implemented above, and I'll get back to that in a second. They just run that. Okay, and so it runs for a minute. Did it finish? Yeah, I think so. And then I'm going to implement that change. And here we go. So all the magic is happening inside that function we just stepped through. Okay, so let's take a look at it here for a second. Now, okay, so we're passing this function U naught and U, which are those arrays, numpy arrays we just created a minute ago. We're passing it W, X, and Vy. Those are the components of the wind velocity field. In this program, those are constants. So I'm saying, well, the wind velocity or whatever it is, the velocity of groundwater transport or whatever, it's constant throughout the model domain, and it has those values. And then I've calculated the time step, and I've calculated dx dy, and that's all I need to solve this expression for t at time k plus 1. So that's pretty cool in concept. Okay, so now the interesting thing about this is I do that whole solution basically in one step for every grid point. And so it's worth unpacking this for a second and seeing how this equation works. So here's U, right? This represents the temperature or whatever at time k plus 1. And I solve for that in the x and y direction, and I do it starting at point 1. So that's the second element in my array. Remember, the first element of the array is index 0 in Python. So this is starting at the second element in the array in the x direction, and the second element in the array in the y direction. Okay, and so I say that's equal to the temperature right now at tk, not tk plus 1. And then I implement the solution. And so here this is W times dt divided by dx, no problem. I could have written that differently, but those are those constants. And then I just have to keep track of my array here, where I am in the array. And so this is U0, 1, 1. That's the same as this one, right? That's the same as this term. So that's like saying tk at ij. And this one is at tk I minus 1 j. So it takes a while to work through that, but that's what's up to there. And then same thing over here for y. So I handle it basically as an array operation to solve this equation for all the grid points. So that's what happens there. Okay, and so that's when I'm just basically calling that over and over again to move this box to the southeast in the positive x and the positive y direction. Okay, just the way the grid's set up here. Okay, now there's a problem with this code. For one thing, it's not going to work if w or v are negative. Pretty sure I can just show that. Let me just make w negative, see what happens. There's my starting condition, and I got to call my function, and I call this, wow, something really messed up. That doesn't look at all like my box being advected away, right? So it's not working when w is negative in this particular implementation, right? So if the wind velocity is negative, the code doesn't work. That equation doesn't seem to work. And same thing is going to be true if I make v negative. I'm not going to bother showing you, but I get a very bizarre answer that makes no sense, right? You could see how the values were going up and down in some sort of random way, making an odd geometric pattern. Okay, the reason for that is you can think of it as this equation, the way I've written it, as representing only sort of what's upwind of you is in the negative x direction or the negative y direction, right? So I've used these these indices -1, references to the index -1 and -1 there to indicate that things are moving from low values of x to high values of x, or low values of y to high values of y. So if you think about it in this differencing approach, if I am only differencing in one direction, I'm only taking that difference, my current position minus the other position in a one direction, it doesn't know that there's a high concentration on the other side, right? So it gets confused, and that leads to a bunch of numerical instability. So even though this is a nice simple solution to the advection equation, it kind of falls apart in a lot of circumstances. There are other issues to it as well that make it numerically unstable. And so when I say numerically unstable, I'm saying that this is not a sensible solution to the advection equation. So somehow my computer simulation just blew up. In this case, it's because of the direction I'm taking in the differencing of that. Okay, so I can solve that, and this is, I'm not going to go through this in turgid detail, but this is how I can solve it for the wind. You can check out these equations at your leisure, but basically I just have to do a bit more algebra to correct for this wind direction problem. And so without going through this in too much detail, people who solve this equation sometimes refer to these f variables as the flux term, and here are the flux terms written out. And so if wx is greater than 0, then that's going to be the expression in the x direction. And if wx is less than 0, that's going to be the expression in the x direction. And if w equals 0, of course, it's not advecting at all. So it's just staying in place. So this is that expression written out for one direction. It's only varying in x, right? And so I've just tossed out all the y terms to make it a little bit easier to understand. And then sometimes people refer to this also as using something called a staggered grid. And you'll notice down here in this 1 plus 1/2 and minus 1/2, instead of +1 and -1, well, we can think about it as if we're trying to get the temperature or concentration on the grid, and we're going to think about Wx and Vy is staggered from that grid, right? It's not really important in this particular application, but that's what that means when people implement it. It's not important here because we're saying, you know, Wx is constant across the model domain, for example. Okay, so here I just implemented those same expressions, and so I'm hoping you take a look at this and you get a sense of how this indexing works for these different equations. This one's a bit simpler to understand, so maybe you could start there. And I implement the same thing here, only worrying about Wx. I tossed out y, so I'm working in one dimension. Everything else here looks pretty much the same. And here's the solution. So I start with the concentration along the x-axis from, I don't know what it was, 0 to something, over, well, at these grid point locations. I assign those to hot values. And I set the wind velocity to be negative because that's what I wanted to implement. So let me better run these in order just to make sure everything goes okay. Yeah, and so the concentration or the temperature is now advected downwind, even if the wind is in the negative direction, right? So this is an improvement in the model, and I can probably change that to, you know, a positive term and rerun it. And it goes in the other direction, right? So this blue line represents time 0, and this orangish line represents the time after all these time steps, 3,000 time steps, or 1,500 seconds, right? So it's moving a long way. Okay, the other thing that's happened is you can see it's looking like it's diffusing at the same time that it's advecting. So what do I mean by that? I mean, it's kind of losing its shape, and it looks like material is diffusing outward from the center. So instead of the line being vertical, the line is now sloping at positive and negative values, right? And that's a diffusion term that's built in to the discretization of these expressions, right? Because I'm looking at it in increments of x and increments of t, I'm going to get diffusion of heat or mass away from the perfectly advected form. So I've got it's basically, in this case, an unwanted characteristic. I'm saying that the box should be a box over here, but it's numerically diffused a bit as I've solved this expression numerically. And in fact, a lot of people refer to that as numerical diffusion, not surprisingly. And usually people regard it as a bad thing. So if we're looking at a meteorological code or a Teffer dispersion code or something like that, we don't want numerical diffusion in the solution. And so people have developed different schemes for dealing with this problem, these two problems really. The one that I wanted the wind to be able to blow in positive or negative directions and still get a decent solution. And number two, I don't want too much numerical diffusion, okay? And so There's a method invented in the 70s, I think, maybe early 80s, the two-step Lax-Wendroff scheme. And here I've written it out for the 1D advection diffusion equation. So basically, this is the same thing. I'm going to implement a different version of this model using the Lax-Wendroff method. And I got this equation out of a book called Numerical Recipes. Here it is, if you can still see my screen. Numerical Recipes. This one is Numerical Recipes in C, and it's by Press et al. It's a book that's been around for 30 or 40 years. They keep on updating it. I don't know, it's been cited something like 15,000 times last time I checked. So it's really an amazingly useful book for scientists because it contains information like this. So Lax, and later modified by Wendroff, published papers on how to solve this expression, the advection equation. I'm not going to go through all the algebra, but you can see what's happening is I've added terms, and I'm sort of thinking about the problem in two directions, right? I'm thinking about it in the forward direction, that is I plus 1 minus I, like in this term, and in the opposite direction, I minus I plus 1. So this will make your head hurt if you think about it too much, and I don't really recommend it, but let's just say that we solved this problem. So here's the implementation of that expression, and I go through the same stuff, and so now this is what the advection term looks like. So it looks like a real displacement, right? I've got the blue curve, it's at time equals 0, and then after time goes by, I changed my scale here for some reason, but as time goes by, I get the orange curve. So those basically look the same. There's still actually a little numerical diffusion, but it's not so bad in this one dimension. And I can, move the velocity in any direction. I'm not going to recalculate it. But so step by step here, we've been developing sort of improved versions of the advection equation to move these particles around in a wind field. And then I'm just going to implement that in 2 steps. And I got bored and I didn't write out the whole thing in 2 steps. But here's my initial condition for a particle. And what I did here was a little different. What's my code? Down here. Okay, so what I did was I said, all right, just like before, here I'm going to have 5,000 steps. I'm going to call this new expression and pass it those variables. Structurally, it's really the same as what I was doing before. But now I've added a term down here. This equation is exactly the same as the equation on my boundary conditions up here. So this is how I set the boundary conditions to make the source at the center. Remember, that's the square volcanic plume injected into the atmosphere or some other thing like that. You can decide how you'd have to change this equation to make it a round plume or whatever. But anyway, we put it up there. And then I just keep calling that expression right here. Here I just wrote it out to make it clear. So every time I keep that plume source there. So it's like as if I've added a source term in each step of the equation. I've said, okay, I'm going to add mass to my problem or heat to my problem every time I step through it. And so when I do that, I get this expression, right? This output. So what's happened is I've created that square at time equals 0, and then I step through it through time, and each time I add more material to the model. So it's as if the volcanic plume is continuously pumping material into the atmosphere or whatever your equivalent problem is, right? So that's all. That's how I use that source term, how I create that source term. And this is what the output looks like. Well, not bad. You can see there's still some numerical instability in this model, right? And so I might have to mess around with my grid spacing, my time step, or whatever to make this behave a little bit better. But it's not doing too badly, and it gets the main point across is that I'm moving material out in the wind field, and in this case, W and V are negative, so it's going to the northwest in my model domain, and it's moving off, and you can see there's still some numerical instability in there, which I would have to address by changing my grid spacing and so on in this model. So I didn't do such a good job in this case of implementing this time step expression. I just kind of threw it out there, but you get the idea. Okay, so that's the 2D advection equation. People spend a lot of time working on this 2D advection model, right? It's interesting that it's an expression that's a little bit unstable. There's a lot of schemes developed to make it more robust and stuff like that. But that's where I stopped for this conversation, because I want to move on pretty quickly to the advection